Dear students, in today's class we are going to see about the flanged beam. So before going to flanged beam, we need to know a term called as torsion. So generally in reinforced concrete structures, the beam will subjected to only the bending moment and shear force. But the torsion is a special case which will occur in our beam due to the flanged beam condition. So if you look at torsion, we are having two types of torsion. One is primary torsion, which will be directly induced on the beam due to load, and another one is secondary torsion, which will be induced in the beam due to the indirect action of the load. For example, if you are considering a torsion in a beam, let us consider a beam like this. So let us consider a beam which is going to be like this, and if you are considering the center of, that is the center line of the beam is here. Instead of applying the load at this point, if you are going to apply the load like this, instead of applying at this point, if you are going to apply the load at somewhere distance, that is away from the center line, that is like this. If you are going to apply the load at this point, then it will lead to twisting in the beam, which will create the primary torsion. So if you are considering the secondary torsion, let us consider an example of a beam like this, and it is going to have a secondary beam. That is, we are going to apply the load only in this beam. That is, let us consider we are going to apply the load at this point. So due to this, what will happen is this beam will try to rotate in this fashion. So it will try to rotate like this. So due to this beam will undergo twisting. So this will be called as secondary torsion, because twisting is created in this beam in which the load is not directly acting. So this is the two types of torsion in our beam. That is, one is primary torsion and another one is secondary torsion. So if you are going to involve torsion in our equation, then we need to solve it by using certain conditions which will be given in our IS 456. So if you take page number 75 in IS 456, they have given certain conditions for shear and torsion. So if you are going to calculate the shear, in normal scenario, we will use only the term Vu. But here if you see, if they have given in some problems, they will directly give the torsion. So we need to use this formula, that is VE represent the equivalent shear, which will be equal to Vu plus 1.6 Tu by B. Vu, here Vu will be the normal shear force which we will calculate from our problem. So here if you look at this, Vu is shear, which will be calculated by using the formula. If it is a simply supported beam, then the formula is WL by 2, that is WL effective by 2. So here Tu, which will be given in our problem, or we will find out from the given conditions. So if you are going to consider the moment, then look here, we will have a formula called as mu1 equal to mu plus mt. Here mu represents the moment which we will calculate from the normal load acting on the structure. So if it is a simply supported beam, then this mu will be calculated by using the formula WL square by 8. Here mt will be calculated by using the formula mt equal to Tu, that is the torsional moment, which will be given our problem, into 1 plus d by b divided by 1.7. So this formula will be used to calculate the torsional moment. So if you are going to calculate AST, we need to use this MT as the final moment of our beam. So here if you are going to consider the shear reinforcement, then we need to use this formula to calculate the shear reinforcement. So which we will see in the upcoming problem. So coming back to our present topic, in flanged beam we have two types of beams. That is, one is T beam, another one is L beam. So the T beam will be provided in the center of the flooring systems. That is, if you are considering a floor like this, then if you are going to provide the beam, then here if you look at this will be the beam which we are going to provide in the center of the section. So this will be having, so let us consider a flooring system consisting of 4 beams. So if you see here, this side we will have only the beam on this side, that is slab on this side. So it will act like a L beam, that is like the shape L. Here if you look at this, then the beam will be like this. If you are going to see it in the cross section, then we will have a beam like this, and we will have a slab like this. So it will be like in the shape of L. So these regions, so here also and here also, the edges of the roofing system which have a beam will look like this. So it will be called as L beam. So if you are considering the center portion, then we will have slab on both the sides. That is, both side of the beam we will have a slab. So if you are going to look at the cross section, then we will have a shape like this. So here we will have a beam, and the top we will have both the sides, because we will have slab on both the sides. So if you look at the shape, it will be in the shape of T. So it is called as T beam, and it is called as L beam. So here in calculating the design, or in while designing the beam, we will have certain scenarios which we are going to see in the upcoming problem. So here if you look at this, if you are asked to draw the components of a flanged beam, then you need to draw like this. Please remember this. So I am going to draw the T beam for our scenario. You can also do the same for the L beam. So in L beam we won't have the slab on one side. So if you are going to consider only this portion, so this will act like a L beam. So here if you see, we are going to provide the components which we are going to be in the beam. So as usual, we will have a beam with stirrups, and inside the stirrups we will have the main reinforcements. So, and also if it is a T beam, then it will have a extra reinforcement which will act as an interaction between the beam and the slab. So here if you see, this will be considered as the main reinforcement, and this will be my stirrup, and this is going to be this overall section. This element will be called as web, and this element will be called as flange. And here if you see, since we are providing at the bottom, it will be called as the tension reinforcement. This will be called as the compression reinforcement, and this will act as this additional reinforcement will act as an integral, that is the element which will help to transfer the load from the slab to the beam. So this will be the transverse, that is, which we will call as transverse steel, which will help to transfer the load from the slab to the beam. So this is the component of a flanged beam. This will be asked in 2 mark question, components of a flanged beam. So while designing the flanged beam, we will have certain conditions which we need to follow as per our IS 4. So while designing a normal beam, we will consider this as the width of the beam, and this as the, from here to here, we will consider this as the, let us mark this point. So we will consider this as the depth of the beam. But while calculating the flanged beam, we need to consider the flanges, that is the portion which is extending beyond the normal beam also will act as a member of a beam. So while designing this, we need to use certain conditions. So here we need to consider the BF, that is effective width of flange. So we need to consider this effective width of flange in while solving the problem. And also we will have BW, which will be called as width of web. This is the web, so this distance will be called as BW, that is width of web. And also if I am going to consider my normal value, that is length of the beam, then in this problem we need to consider the depth of flange, that is DF. Here this portion will be called as DF, that is depth of flange. And this overall depth, this will be considered as the depth of the overall beam. So we need to consider all these values in our problem. So as in our IS 456 code book, if you look at this in page number 37, they will give formula to calculate the value of BF, that is width of the flange. So here if you see BF, then the formula is L0 by 6 plus BW plus 6DF if it is a T beam. If it is a L beam, since this beam will have only flange on one side, so here if you see half of this value, that is L0 by 6, that is L is length of the beam, so of by 12, 6df it is 3df. Since the width of the web, that is which is going to be remain the same, so we are directly taking as bw. So if you are going to calculate this, then we need to know the value of L0. L0 is nothing but the distance between the points of zero moments in the beam, that is where the moment will be zero. So if you are considering a simply supported beam, then the moment will be zero. So let us consider this example and I am going to solve this. So if I am going to consider a simply supported beam, then the moment will be zero only at the end of the beam. So here this L0 will be considered as the actual length of the beam. So if it is a continuous beam, then they have given the condition for consider, please look at this note, for continuous beam and frames, L0 may be assumed as 0.7 times the effective span. So if it is a simply supported beam, then L0 will be simply supported, then the L0 will be same as L. But if it is a continuous one, then the L0 will be equal to 0.7 times L effective. Here also L effective length. Here also this will be considered as the L effective. So L0 equal to 0.7 L effective. So based on that, we will calculate this L0. We know the value of BW, that is web width, and DF is depth of the flange. We know the thickness of the slab. So we know these two values. This L0 will be calculated based on this condition. So based on this, we need to solve our problem. So here in solving the flanger beam, we will have two main conditions. So if you take page number 96 in IS 456, in the G2 they will give you as flanger section. So we will have two conditions. First one is for XU less than DF, that is if the neutral axis depth is less than the depth of the flange, then the moment of resistance may be calculated from equation given in G 1.1. That is, we need to design when XU is less than, when XU is less than DF, then the beam can be designed as, then the flanged beam, then the flanged beam can be designed as normal rectangular beam, then it can be designed as normal rectangular beam. So this is the condition which we will use, that is this is the first condition in design of flanged beam. So this will be my first condition in design of flanged beam. So once again I am repeating this concept. If I am going to design the flanged beam, then the first condition I need to check is whether it is XU is less than DF. If it is true, then the flanged beam can be designed as normal rectangular beam. So as per this condition, but if XU is greater than, that is if the XU value is going to greater than DF, which means that is the XU, that is the neutral axis is going to be within the web of the beam, because it simply represents this scenario. So if it is less than DF, then the XU, that is neutral axis, will lie in this area. So we can design it as a normal rectangular beam. But if it is going to be fall in the web, then we need to use the condition which was requested or which was recommended in our IS 456. That is, if the XU value is greater than DF and DF by D, that is depth of flange divided by effective depth, is less than 0.2, then we need to use this formula, mu equal to 0.36 XU max by D, 1 minus 0.42 XU max by D, FCK BW D square, plus 0.45 FCK BF minus BW DF into D minus DF by 2. So based on this formula, we need to calculate the moment, and based on that we need to calculate the AST. So you will also have another one doubt, sir, if DF by D is going to be greater than 0.2, then what I will need to do? So when DF by D exceeds 0.2, that is DF by D is greater than, DF by D is going to be greater than 0.2, then I need to use this formula. Here if you see, the only difference, before we have it as df, here we are having it as yf. This yf sorry, this yf value will be calculated by using this formula, 0.15xu plus 0.65 df. So based on these three formulas, we need to solve our problem. That is, we need to solve our flanged problem. Now we are going to see a T-beam problem.